Solution of system of linear equations using inverse of a matrix. Let me take a system of linear equations of two variables, two equations. For example, let me take in general a1x plus b1y equal to c1 is one equation, a2x plus b2y equal to c2 is another equation. First of all, we'll write the equations in this standard form and then rewrite it as the coefficient matrix I call. Take the elements of the first column, that is a1, a2, and then the coefficient of y in the second column, b1, b2, multiplied by a matrix of order 2 by 1 xy equal to c1, c2. That is, you rewrite the system of linear equations, two variable, two equations, or similarly could be three variable, three equations in matrix form. Let us verify is the information same as given algebraically. Both the informations should be same. How do you multiply row to column? So it will be a1x plus b1y equal to the c1, and then you multiply with the second row, you will get a2x plus b2y equal to c2. So yes, the given information system linear equation when written in this matrix form is exactly the same. In short symbols, it may be written as A for matrix A1, B1, A2, B2, capital X for matrix XY, column matrix XY or XYZ in case it is of three variables, and for the constant C1, C2, I use symbol B matrix. And then you pre-multiply on both sides by A inverse, it will reduce to the variable matrix X equal to A inverse into B. You work out A inverse into B and you will get the solution by respectively equating to the X, Y, Z. But remember, please take a note here that here with A inverse it has to be pre-multiplied and not B into A inverse, because here A was on the left, so multiplying both sides on the left, that is very important. And now we'll explain it with the help of an example. Let me first give you the consistency rule for system of linear equation. Here you run, please note down consistency of the system of linear equations, system of linear equations. You know that we can work out the value of variable matrix X as A inverse B provided A inverse exists. Now what is the definition of A inverse? A inverse is 1 by determinant A into adjoint A. Now case 1, if A is a non-singular matrix, if A is a non-singular matrix. What do you mean by a non-singular matrix? That if determinant A is non-zero, is not equal to 0, then A inverse will exist. Obviously, then A inverse exists, and if it is so, then we can solve the system linear equation, and we say that the system of linear equations has a unique solution. It has a unique solution, and of course the system is consistent. The system, rather I should write this way, system is consistent and has a unique solution. That is case 1. Now case 2, if A is a singular matrix, if A is a singular matrix, that is if determinant A equal to 0, then there will be two cases. Number 1, if determinant A is 0 and then we further work out adjoint A, of course A inverse does not exist, but still we can work out adjoint A, then find the value of adjoint A into B. What is B? The constant matrix. In case it is not equal to 0, we say the system is inconsistent. System is inconsistent and has no solution. and B, the B of what? When determinant A is 0. If the product adjoint A into the constant matrix B is also a 0 matrix, then also the system of linear equations is consistent but with many solutions, infinite many solutions. So I repeat that to check the consistency of system of linear equations, you work out the value of determinant A. What is determinant A? What is A? A is the coefficient matrix. So work out determinant A. In case it is not equal to 0, we say the system is consistent with unique solution. In case it is 0, then you work out adjoint A, and in case adjoint A into B, the constant matrix, is non-zero, we say the system is inconsistent and has no solution. In case it is 0, that is adjoint A into B is also 0, we say system is consistent with many solutions. Now let me take an example to illustrate you how to solve a system of linear equations using matrix method. I take an example having two variables and two equations. The instruction is solve using matrix method, or of course using the inverse of a matrix. That is what is matrix method. The system equations is given to be 2x plus 5y equal to 1, and the second equation is 3x plus 2y equal to 7. First of all, you rewrite it in matrix form. That is, the coefficient matrix 2, 5, 3, 2 multiplied with the variable matrix like this xy equal to 1, 7. 1, 7. To the first matrix you call A, to the second you call X, and the constant matrix is B. Pre-multiplying by A, it will reduce to X is equal to A inverse into B. Or what is X? X is the variable matrix XY, and in case it is a 3 variable, we should write XYZ. On the right side you have A inverse, and what is B? The constant matrix which is in the present question 1, 7. So first of all, theoretically, we rewrite the question till here. Okay, all these steps we are supposed to repeat. And now it is merely a matter of finding A inverse and replace. I write again what is A. A is the coefficient matrix, that is 2, 5, 3, 2. So how do you work out A inverse? You know the definition of A inverse as 1 by determinant A into adjoint A. So at least what is the value of determinant A here? Determinant A, you know, it will be 2 into 2, 4 minus 15, which will be minus 11, we'll need later. And now let me work out adjoint A. By now you know adjoint A is the transpose of the matrix obtained by replacing each element by the corresponding cofactor, and for the main diagonal you have just to interchange, so it will be 2 and 2. For the other diagonal you change with the change sign, interchange the elements with the change sign, so you will have a minus 5 and minus 3. Instead of doing it directly, because I have written transpose, you know what is the cofactor of 3? 5 with a negative sign. And what is the cofactor of 5? Minus 3. And now you take the transpose. So you get 2 minus 3 minus 5, 2. So that is the value of 2 minus 5 minus 3, 2. That is the value of adjoint A. And now using the definition of A inverse is 1 by determinant A into adjoint A. That is 1 upon negative 11 times 2 minus 5 minus 3, 2. And now you replace this value of A inverse in 1. So from 1, the value of XY matrix is A inverse. And what is A inverse? We worked out as negative 1 by 11 times adjoint A we worked out as 2, negative 5, negative 3, 2 multiplied with the constant matrix 1, 7. So take the product of the constant matrix, keeping for time being minus 1 by 11 as such. First to take the product. You know how to take the product? Row to column. So it is 2 minus 35, and then you repeat the process with the second row to the column, and you will get negative 3 plus 14. Work it out, you get negative 1 by 11, and the matrix will be 2 minus 35, that is minus 33, and 14 minus 3, that is 11. And now dividing inside by minus 11, so you get 3 minus 1. And what do you have on the left? The matrix XY. So matrix XY, the quotient matrix, equal to 3 minus 1, which implies the value of X is 3 and the value of Y is negative 1. Just to make sure that our result is correct, you are advised to put the value of 3 and minus 1 in the given equation and see that satisfies, that proves that your answer is correct, though formally it is not required. If I replace in the first equation, you get 3 into 2, 6 minus 5 equal to 1, correct. In the second equation, 3 into 3, 9 minus 2 into 1, 2. So it is 9 minus 2, 7. Yes, the value of X and Y satisfy both the equations. So we are sure that our answer is correct.